Okay, so the title of 4.3 is Riemann sums and the definite integral. So we talked about all parts of the definite integral yesterday, and from the classwork I think it seemed to go smoothly. Now let's talk quickly about a Riemann sum. So a Riemann sum is any geometric approximation of the area of a region. Why do we need Riemann sums? A function is not always provided, and therefore we wouldn't be able to find the exact area under a curve. Okay, so exact areas cannot always be determined. So we still need valuable tools to approximate areas, and that's what the general term Riemann sum represents. Okay, so approximations on a closed interval can be used or can be found using rectangles or trapezoids. And you will study trapezoids later in the chapter in section 4.6. And we've begun to talk about rectangle approximations. So if you're looking in the textbook, what does this notation mean? Delta x is the width of the interval. F of x sub I, this is just the height of the interval. And where does the height come from? We can look at the left endpoint, we can look at the right endpoint, and today we're going to look at the midpoint. So we know with a left endpoint approximation, we always start at f of a, regardless of whether the left endpoint will be our upper sum or our lower sum. A right endpoint approximation, we start at f of a plus delta x, so whatever the width of the interval is. And now for a midpoint approximation, so think about a function between a and b. If I'm looking at an interval, so this space here would be delta x, then what would the midpoint of this interval be? Okay, and the midpoint just means if we drew a rectangle to approximate the area, well then the height of the rectangle is going to intersect the function at the midpoint of the interval. So where does this value come from? It's the width of the interval divided by 2. It's the middle of this interval here. So for midpoint approximations, we always start at the value f of a plus delta x over 2. We can't start at the left, we can't start at the right of the endpoint, or of the interval. We start at the middle of the interval. Now when you're asked to determine upper and lower sums, that always means look to the right and the left endpoint of the rectangles, and then we've talked about this. Okay, upper and lower sum depend on the behavior of the function, whether the function is increasing or decreasing, and this relationship is important, and you would have seen on number 8 from your quiz that you took. If you're asked to find upper and lower sums, you have to understand the behavior of the function and know if the right or the left is the upper or lower sum. Okay, so page 269, number 73. Use the midpoint rule with n is equal to 4 to approximate the area of the region bounded by this function, the x-axis, over the interval from 0 to 2. So midpoint rule. Delta x is determined the same way, b minus a over n. So the width of each interval is going to be half a unit. Now, where do we start for the function values? A plus delta x over 2. A is equal to 0. Delta x is equal to a half, and then we're dividing that in half as well. So the first value we plug into the function to get the height of the rectangle will be a 4th. So to set up the Riemann sum, and again a Riemann sum, just a geometric approximation, delta x, f of 1/4, and then the next value will come from 1/4 plus delta x, because we need to keep the width of the intervals the same. The width of the intervals doesn't change from 1/2 of a unit. So 3/4 plus f of 5/4 plus f of 7/4. So between each x value is delta x. 1, 2, 3, 4 y values corresponds directly to the 4 rectangles that you were told to approximate the area. So for your homework, find the approximation. So evaluate the midpoint sum. Now what's nice about the midpoint, if you're asked to find the midpoint approximation, this is it. There's no left endpoint, right endpoint for midpoints, so it's just one setup and therefore one answer for the approximation. Okay, number 45 from page 279. Use the table of values to find lower and upper sum estimates of this function. Assume that f is a decreasing function. So another reason why approximations are valuable. We don't know anything about the function except for 6 specific values and what their values of the function are as well. Alright. F is decreasing, so the left endpoint is going to be our upper sum. Now, where does delta x come from? Delta x comes from b minus a, and then look at we have 1, 2, 3, 4, 5 intervals here. So using the table of values is going to determine how many intervals we have to approximate. So the width of each interval is going to be 2 units. Okay, so what are our intervals? Our intervals are from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So when we look at the left endpoint approximation, which will represent the upper sum, delta x, start at f of a, so f of 0 plus f of 2, f of 4, f of 6, f of 8. So now we don't have a function to plug into to find the y values. We get them from the table. F of 0 is 32 plus 24 plus 12 plus negative 4 plus negative 20. So negative 24, they cancel each other out, and we have 2 times 44. So the upper sum will be 88 units. So the lower sum will come from the right endpoints. 2 to 2, 2 to 4, 8 to 10. Alright, so delta x is still equal to 2 units, so 2. Now we start at f of a plus delta x, f of 2, f of 4, f of 6, f of 8, and then f of 10. And same things remain consistent. The middle values remain the same for the upper and lower sums. We know the left sum starts at f of a, it excludes f of b, and then the right sum excludes f of a and ends at f of b. So using the table of values again, they cancel each other out. 12 minus 36, negative 24, so negative 48. So the area is between negative 48, which was our right endpoint approximation, and 88, which was our left endpoint approximation. Now, after the classwork on the first day of this, a negative area, quotations, a negative area just means that the region would lie below the x-axis. Okay? That's it, and I'll see you tomorrow.